All right, let's dive right into this explainer. Today, we're going to explore how we can finally dismantle the traditional rote memorization approach to teaching fractions. I mean, if you've ever heard that collective, audible groan from a classroom the second the word fractions goes up on the whiteboard, well, you know exactly why we're here today. We're drawing directly from Chapter 13 of Teaching Student-Centered Mathematics to completely reframe how we build conceptual understanding across all four math operations.
We all know the shared frustration of those endless fraction rules, right? So our central question today is looking at why misapplying whole number rules creates so much actual math trauma for our students. Think about it for a second. We literally just hand students rules like invert and multiply, or find a common denominator, without giving them any context whatsoever. The result? They overapply these rules, they guess at when to use them, and they completely lose sight of the actual math.
Here's our roadmap for today's explainer. First, the fraction dilemma. Second, 4 steps to understanding. Third, meaningful addition and subtraction. Fourth, visualizing multiplication. Fifth, demystifying division. And finally, transitioning to standard algorithms.
Let's kick things off with Section 1, the fraction computation dilemma.
You know, the research is crystal clear on this. Until students understand fractions in a meaningful way, they're going to consistently make errors by overapplying whole number concepts. But here's the real game changer. When we reframe those mistakes not as total failures, but as logical yet flawed overapplications of whole number rules, everything changes. Like, when a student sees 4/5 plus 4/10 and they write down 8/10, they aren't just making a random careless error. They're actually just doing what worked perfectly for whole numbers, adding straight across. So the intervention here isn't to just cross it out with a red pen, it's to bring out a number line or a fraction strip so they can visually see exactly why adding denominators makes no logical sense.
Moving right along to Section 2, 4 steps to understanding.
To fix these common errors, researchers like Siegler suggest a very specific 4-step sequence. Think of this as your ultimate sense-making toolkit that takes abstract symbols and turns them into logical, tangible concepts. Step 1, give them a real-world context. Step 2, have them defend their solutions using visual models. Step 3, make them estimate before they ever calculate. And Step 4, tackle those common misconceptions head-on, rather than just hoping they quietly go away.
Okay, on to Section 3, meaningful addition and subtraction.
By using authentic contexts, like, say, doubling a real historical recipe, we immediately anchor the math in relatable, real-world measurement situations. The source material actually highlights an amazing example using a Civil War recipe for northern brown bread. Just imagine a student needing to double a recipe that calls for fractions of a cup. They aren't just blindly pushing numbers around on a page anymore, they're solving a real tangible problem. They start asking themselves, okay, if I have 2/3 of a cup of molasses and I need twice that amount, how do I actually measure that out? They might physically picture 2 1/3 cups and then another 2 1/3 cups, organically realizing that they now have 4/3. It's absolutely brilliant because the context itself prevents them from making that classic mistake of just adding denominators.
Now, take a look at Kieran's naive approach here. If a student tries to add half a small pizza to a third of a large pizza, and they literally draw one small circle and one giant circle, their resulting addition is going to be completely skewed. But this opens up a fantastic opportunity for a gentle correction about how the whole must be exactly the same size for the fractional parts to be combined meaningfully. It's such a massive light bulb moment when they realize, oh wait, you can't just mix and match different sized wholes.
So before we even touch common denominators, we absolutely must use estimation to ask one simple question. Does this answer actually make sense? For example, if a student is asked to add 7/8 and 5/6, they should immediately recognize that both of those fractions are really close to 1. So obviously the answer has to be a little less than 2. If they just blindly calculate and get 41/24 without knowing what that even means, well, the math is lost. Building this simple habit of estimating first stops wild guesses right in their tracks. It literally prevents absurd answers before they even happen.
Which brings us to Section 4, visualizing fraction multiplication.
Guys, there is a massive conceptual shift when we move to fractions. With whole numbers, multiplication just means equal sets, like 3 sets of 5. But with fractions, we're talking about finding a part of a part, something like 1/2 of a length of 6. Simply changing how we talk about the operation fundamentally changes how students visualize it in their minds.
And here is where we completely shatter the whole number assumption that multiplication always makes things bigger. When you model 3/5 of 2/3 using a grid,
Students physically see that the overlap, the actual answer, is a smaller slice of the whole. It's such an incredible realization for them to see that the product is actually quite a bit smaller than either of the original fractions. By clearly defining exactly why denominators change here, but not in addition, we eliminate the blind memorization of just multiply both the top and the bottom. Listen to this. In addition, we're just counting parts, so the part size stays the exact same. But in multiplication, we're taking a part of a part, so the actual size of the pieces changes. Making this specific distinction explicit clears up so much confusion.
All right, Section 5, Demystifying Fraction Division.
I love this quote. Invert the divisor and multiply is probably one of the most mysterious and confusing rules shared in elementary mathematics. It just perfectly captures the trauma of traditional math instruction, and it signals exactly why we need our sense-making framework. When we just hand students a magic trick to flip the second number and multiply, we completely strip away all mathematical reasoning.
Visualizing these equivalent expressions is so crucial because it constantly prompts sharing questions, like how much for one, or how many for one. Let's bridge the gap here. If you have 5 sandwiches shared among 4 friends, a linear model shows the division of 5 divided by 4. Let's walk through that slowly. Taking 5 whole things and splitting them 4 ways means each person gets exactly 5/4 of a sandwich. Connecting the division expression, 5 divided by 4, directly to the fraction itself, 5/4, is a massive light bulb moment for learners.
Now here's a trap so many fall into. Let's say a student has 5/3 pounds of fudge and divides it by 1/4. Emphasizing the exact unit of the remainder ensures meaning isn't lost in that final step. Often students will perform the division, get a remainder, and have absolutely no idea what that remainder actually represents. Is it a fraction of a pound of fudge? Is it a fraction of a serving? Pinning down the exact unit is absolutely essential for true sense-making.
Finally, let's look at Section 6, Transitioning to Standard Algorithms.
I want to be clear here. We aren't abandoning formal math. We're simply redefining how we arrive there. The goal isn't to draw pizzas and number lines forever, right? Standard algorithms are incredibly elegant, but they have to be introduced as the final formal step that naturally emerges from weeks of conceptual understanding. When students have spent time estimating, modeling, and discussing their own invented strategies, they just start to notice the mathematical patterns organically. The algorithm then becomes a fast, efficient shorthand for what they already understand deeply.
So I'll leave you with this provocative thought. If standard algorithms are the destination, isn't conceptual understanding the vehicle that actually gets us there? Let's stop relying on mysterious tricks and start building true foundational sense-making in our classrooms. Thanks for joining me on this explainer, and I'll catch you on the next one.